Caching is a very important but also complicated part of software development, and I wanted to put together a video for beginners to get introduced to some caching concepts in C# and .NET. Hi, my name is Nick Cosentino, and I'm a Principal Software Engineering Manager at Microsoft. This video is going to be a little bit different compared to some of my other ones, given that we're going to be looking at caching concepts, but we're going to cover a lot of ground. We're not going to go super deep, super technical, but just look at a high level just so we can cover some of the basic concepts. If you're a C# developer and you haven't really been exposed to caching, it's still sort of a new concept for you, then I'm hopeful that this video will give you some of that understanding. If you've had more experience with caching and you've worked with distributed caches, this is probably going to be a little bit too basic for you, but we're going to be exploring some different libraries and some of them will support distributed caching. So if that sounds interesting, just a reminder to subscribe to the channel and check out that pinned comment for my courses on Dome Train. Now let's jump over to Visual Studio and get started with a very simple example. On my screen, I have the sample weather forecast application that we get when we're creating a new project in Visual Studio, but I've modified it a little bit just to reorganize some of the content, and from here we're going to be talking about a very simple starting point. Now, why do we want caching in the first place? This is probably something that's worth answering because, again, if you're very new to the concept of caching, you might be wondering, why do we even care? Well, there's many benefits to caching, and like I said in the intro to this, there's also a lot of complexity that comes along with caching as well. Some of the benefits that we get with caching include reduced latencies as well as reduce load on other services. When we're talking about big, complex distributed systems, having low latency can be incredibly important, as well as reducing load on other services. These two reasons together can be a huge motivation to introduce caching. But given that caching has so much complexity that comes along with it, it's not necessarily something that you want to rush into, especially if you're a beginner. And that's why I wanted to take this starting point to go look at this very simple application, put in a bit of a delay, and then see how caching can start to transform some of the performance characteristics. Now, for the weather forecast application, what I've done is I've introduced a day of the week. It's not really going to matter. We're not actually using that to do something based on Monday, Tuesday, Wednesday, whatever, but I just wanted to change the API so that we can talk about caching a little bit more as we go through these examples. But one thing that I am doing is I'm introducing this delay here, and it's going to be 1 second, and that's going to be so that we can simulate if we had to go to a database or another service to get the information for the weather forecast. This is going to simulate on the request path that we're going to have some additional delay. This right here, of course, is just the delay, but that's where I want you to think about that we might be having to interact with something else. Again, that could be a database, that could be some other microservice or whatever it has to be that's not necessarily just in process like we're dealing with here. We have to be a little bit creative, but that's going to help us illustrate some of these characteristics. So other than that, there's not really a whole lot to look at right now, but I want to run this and just kind of show you what we're going to be exploring step by step as we start to tune things with caching. So let me press play. Okay, so in order for us to hit this API, you can see that I have /weather forecast, and then we have to pass in the parameter for the day of the week. Like I said, though, this day of the week isn't really going to be important. It's just going to be used in the examples as we go forward with caching. Now, because I have that 1 second sleep, if I press enter here, we can see it's going to have a bit of a delay before we get new numbers. I'll do it again, and I'll do it again. And you can see that as a user, if you were trying to use even something like this to load a web page, that's going to be kind of crappy to have to wait a full second. And if you think about more complicated services that have to do requests like this, of course, having a delay of a full second is not really that great. And this gets even worse when we're layering in more complexity. But something that I wanted to show you is what happens when we start to do things in bulk. So let me go ahead and go back to Visual Studio. I have this bit of code here that I'm going to uncomment. It's going to be a little bit nasty. It really wants me to have an await out the front here, but I'm not going to actually leverage that when we go to run this, just to make the warnings go away as I talk through. This is just a bit of a hack to kind of simulate a whole bunch of traffic. So I'm going to wait for 5 seconds, and that means the app should be up and running. Then what I'm going to do is use the HTTP client factory, and this is going to allow us to make a whole bunch of HTTP clients, and all that I'm going to do is in a loop for 1,000 different tasks, I'm going to start hitting our service, and then we're going to wait for all of them to finish. The result of this is we're going to see in the console that there's a whole bunch of web requests, and we'll start to see the responses coming back, and we're going to see the delay that it took to actually get that request to finish. Something that we'll notice, and I'll show you in just a moment here, but something that we'll notice is that we're going to see all of these tasks piling up. So that means that the latency in terms of finishing that request is going to keep growing. And that's just because there's a whole bunch of requests to serve. If we think about it, each one of these is supposed to delay really only 1 second, and then the work that's actually done on the rest of the request path is pretty lightweight. So it wouldn't be so unusual if we saw all of these tasks that we're going to go fire off take roughly 1 second, but that's not what we're going to see. It's going to be significantly worse. So I'm going to go ahead and press play. We're going to watch in the console instead of the browser, and we should see a bunch of these fire off. Then I'm going to sort of pause so we can look in the console and start to see some of the tasks coming back. I'm going to switch over here to our application, and we should start seeing these all pile in. And in just a moment, what I'm going to start to do is start seeing if we can get some results coming back. So if I start to highlight here, just to pause it a little bit, you can see end processing HTTP request after 7.5 seconds, right? This one's about 4 seconds. This is 6.5. This is 7.5 seconds. Over 8 seconds here. So that sleep that I was talking about, that task delay of only 1 second, that's absolutely not what we're seeing here. We're seeing so many requests come in that it's actually introducing a lot of latency for our system. And really, this is a very simple API request, right? So it's not like it's actually going out and doing anything complex. We're not actually relying on any services or anything external, but just to sort of simulate this very basic behavior, you can see that just having a lot of requests like this is going to be pretty detrimental to this service, right? The latency is really just through the roof. So we can do better than this. What I'd like to do now is start talking about caching. And I should mention that as I go through all of these examples, this is going to be a longer video. I mentioned that in the beginning. I'm going to put a playlist together, and this playlist is going to contain more succinct videos on some of these topics. So I'm going to go very high level through some of these just for a beginner view at a lot of them, but I will have other videos that you can check out in that playlist where we can do a little bit more of a deep dive. There'll be a lot more pointed in terms of what we're trying to tackle, but this one is just to start comparing and contrasting, and we'll get a little bit more complicated looking at different packages and different ways to cache as we go through this entire video. To start things off, the very basic type of cache that we can look at is just a dictionary. Now, if you have a little bit more knowledge about caching, you might say, Nick, well, I don't think a dictionary is going to be a good idea here. And you're right, but I think it's going to help us get started in looking at some performance gains. Truly, a dictionary is just a really simple way that we can get a little bit of caching going on. So what I'd like to do is introduce this cache, and then we can go back to the browser and see some of the behavior that we get. Okay, so on line 11, I've introduced a dictionary here, and it's just going to be keyed by the day of the week, and it's going to have the collection of weather forecasts, okay? So I realize that this whole setup here is kind of awkward, right? It's not actually, this forecast down here is actually doing 5 days at a time. Not really the point. The point is that we're going to have a cache that's by days of the week. Just bear with me for this example. And what we're going to do is see, now that we have this caching logic here, how that's going to improve some of our performance. So to explain what's going on here, instead of just creating that weather forecast, what we're going to do first is check if our cache for the day of the week has a forecast for it. And that cache, like I said, is just going to be this dictionary up here. If you're not familiar with what a dictionary data structure is, I do also have some beginner YouTube videos available you can check out that look at different types of collections in C#, and I do cover a dictionary, so you can check that out if you want to see more details. I won't really dive into that in this video. We're going to check if the cache has a key for the day of the week, and if it does, this try get value will give us that value for that key. But if it doesn't, which is why we have the exclamation out the front, we're going to say, okay, go create that weather forecast for us, then we're going to cache it. That means, ideally, the next time that we go run this code, we should be able to go get the value back out of the cache. And that means the second time through, we shouldn't have to go into this if statement at all. And that's because it's going to be inside the cache and we can return it directly. Let's go run this and see what the performance characteristics are like in the browser. Okay, so if you recall, the first time I press enter to go hit our API, we should see a delay of about 1 second. And there we go, so new results. But if I press enter now, it might be difficult to tell, but it's finishing basically instantaneously, right? To me, as a user hitting this page, I'm not really seeing any delay at all. It's just going through. So this is an example of caching, right? That's the huge benefit that we get because now our latency is reduced dramatically. And if this was a service call that we had to go make to some other resource, we're not spending more cycles trying to go do some other execution and, cause other resources to have to spin up and do other work. There is a trade-off though, and that's now that we're using some memory to be able to shortcut that, right? So in this case, it's a pretty good trade-off, and that's because to store this in memory for us is very lightweight. If we think about the size, like the footprint size of memory in terms of what this cache is going to hold, if we're just talking about the days of the week and then some of these forecast entries, this is a pretty small footprint, right? We're talking about 7 days of the week. And I know, like I said, this is kind of confusing because the way this weather forecast app to start with was probably supposed to do 5 days at a time. But if you just imagine that this is the forecast within the day for an example here, then we could imagine that we might see something like, I don't know, 7 days of the week times like maybe there's 4 or 5 different forecasts within the day. So you might see something like 28 to 35 entries. It's a pretty small price to pay in memory to be able to have this return very, very fast. But if we were caching other data, something that might have tons and tons of records, for example, at work, when I'm dealing with caches, we have things that have to cache things like IP addresses. But like, how many IP addresses are we talking about? It's not like 10 or 100. It could be millions. It could be millions and millions of different records that we have to cache. And that means that all of a sudden the footprint isn't like a couple of records in memory. We actually really have to start thinking about resources, and that's going to be an interesting trade-off when we're building different systems. This is something to think about when you're working with caches. It's going to be a trade-off, and this is the case for basically all things in software engineering. Now, when we're using a dictionary like this, there is a few different problems. And I'm not going to be able to highlight all of them, but I want to show you one thing that can happen when we start introducing scale to the number of requests. So I'm going to go back and put in this little bit of code that spams our server with a bunch of requests. And if we get lucky or unlucky, we'll see what kind of problem shows up when I go run this. Okay, so we're going to go run our server and we'll start hitting that API and we'll see if we can trigger this bad behavior. And there it is. So we have this problem and it says an object reference is not set to an instance of an object. And it's going to be a very misleading exception when you're dealing with this kind of thing. The reason I'm saying it's misleading is even when I was getting this video set up with these different examples, this isn't even the exception I was seeing. I was getting a key or an index out of range. And the reason that we're seeing this exception, or the ones that I was seeing before I started recording, is because this is actually what's called a race condition. A dictionary in C# is not thread safe. And what's happening is we're now running this web server, and we have many different threads that are trying to hit our web server, and they're saying, give me the data, give me the data. And our cache is sitting there going, hey, no problem, like, let me get that for you. But what's actually happening here is that, like I said, there's a race condition. So as we're reading the cache, we're also updating the cache as well. And that means that we're going to have this little bit of an issue that is what we're seeing here. So if I were to go look at the details of this exception, the stack trace is going to be inside, right? So it's trying to insert. Like, why is this a problem, right? And it's just a problem because, like I said, it's racing. We have multiple threads trying to do something, and this collection is not designed to be sort of used across different threads like this. So there's a solution, and I'm going to stop this for a moment, and we're going to see that we can basically fix this particular problem pretty easily. There's something called a concurrent dictionary. And you'll see that if I add concurrent here, and then I use system collections concurrent, notice how none of the other code broke, right? Like the cache, the APIs that we call here to get the value, to add it back in, they still work. So I'm going to go ahead and run this again, and it's not going to guarantee the fix when we go run this, because it is a race condition we were seeing before. Maybe we don't hit the same race condition, but hopefully you believe me that when we go to use this, it should solve this particular problem. So I'll press play again. We will pull this up and we'll start watching these requests come through. So it's really nice as we start firing all of these off. And this is still running. You can see in the console in the bottom, it might be hard to see that the scroll bar is actually moving, but this is working. One of the tricky things, and I realized my example might be a little bit misleading from earlier, is that when I scroll back up, I did see some of these requests that were taking a little bit longer than they probably should, right? I think this is probably just piling up because I'm making the requests from the same process. So I apologize that this example might have seemed a little bit misleading, but if I scroll down, you can see down here that we have these sort of times coming back, right? So, 50 milliseconds, 50 milliseconds, 78, like that's why when I was in the browser, I could press enter very fast. So if we go to the bottom here, you can see that it's all done processing. It's gone and made 1,000 different requests and they've finished. But something else that explains, if I scroll back up, we're going to see this actually in a little bit more detail when we get to some of the more advanced caching libraries, is that these times, this is actually something that's happening because when we have multiple threads trying to check the cache, if you think about each thread trying to enter that execution, you have, let's just pretend we have two coming in at the same time. When they're at the exact same time, what's happening is one's checking the cache and saying, hey, do you have that? No? Okay, like let me go generate it. But at the exact same time, another one's doing that. And because we have a whole bunch of them in parallel going to do that, they're basically doing what's called like a stampede. So they're all trying to go into the cache sort of logic and nothing's stopping them all from entering. So what would happen is if there was nothing in the cache, if this was a downstream service and we had, like, just to do a quick check, right? There's one here that's taking a while, 2, 3, 4, 5. There's way more than 10, way more than 20. If I keep scrolling, you can see there's more and more of these. These would technically all be downstream calls to some other service. So instead of our cache protecting those things, what's actually happening is that our cache is going, I don't have the entry. Hey, all of you, you can go check downstream. We'll go fetch the data, do whatever processing, and then we'll put it into the cache. So we can do a little bit better in some of the things that we'll see coming up. One of the challenges that we might have with a dictionary or a concurrent dictionary, maybe not really for the weather one that we're looking at, but in terms of how much we're storing in a cache, we may want to limit that. And the other thing is that we may want to have more control over how long those things live in the cache. When we're using our dictionary data structures, we don't really have control over either of those things unless we start to build some of that logic around the cache itself. So out of the box, neither of those two collections really do that for us, but we could do things like trying to store like the timestamp information. We could try to check the count of the dictionary, but there's other things that we can use that already have this logic available to us. So one of the libraries that I've really enjoyed using in different projects that I built with is called BitFaster. So BitFaster has this caching library, and just to show you when we go over to the project, let me click over here. You can see that I'm using BitFaster caching 2.5.2. So a bit of a spoiler alert for some of the other things that we're going to be looking at, but you can see at the top here that I'm using BitFaster caching LRU. And that's because the cache that I want to look at here is this fast concurrent TLRU. So if you hover over it, BitFaster has a really good set of documentation for how their different collections work. For me, this is really helpful to get an understanding. So when I start to pull information into memory, I'm storing it in this collection. Like, what's actually happening here? Like, how do I control the stuff that I'm putting in, right? So it has a bit of an explanation about the algorithm, right? And then it explains how it's based on some of these other comparable things. So if you want to go read more about these, understand how the actual caching algorithm works, you can go ahead and do that with respect to some of the internals. But at a very high level, the things that we're going to be looking at are this capacity. So just to kind of write it out, there's a capacity, and then this other part is how long we're going to keep things in the cache. So we can actually control both of these things. That means that if we tried to keep caching more and more items, if we went over 7, and in these examples, the day of the week, I'm always setting it at 1, so there should only ever be one thing in the cache. But again, just to kind of walk through, if we were to go over 7 items, what would happen is that it would evict the one that it needs to based on the algorithm we're using. So it has a capacity limit. There will never be more than 7. And then there is this duration as well. And that means that the entries in the cache will expire. So I have that set to be 3 seconds. And what we can do now is actually go to the browser and see that we have more control over the behavior of this API. It's not just going to be every time I press enter in the browser that we're going to have this immediate response. In fact, we'll see that the data refreshes periodically, and that period is 3 seconds. So let's go ahead and run it. Okay, so when I go to press enter here, we should see this one take around 1 second. There we go, new set of data. But if I press enter again, enter again, enter again, see on that last one, it took a little bit longer and it gave us new data. So doing it again and again and again, and then now another set of data. So the way that this cache is working for us is that it's actually expiring the time after 3 seconds. What I'm not doing is exercising sort of this code path. So if I do 3, I should have used Postman or something else to go simulate this, but you can see that as I was doing these other numbers, I don't know if I can do this fast enough, but if I tried to go back to 1 was still cached, right? It's a little bit too hard to show you in a video, but the point here is that I'm able to sort of cache these other entries. If I were to somehow go over 7 in that period of time, we could actually see that we'll evict the ones that were at the beginning. That's how BitFaster caching could be used if you wanted a little bit more control. But like I said, I'm just going to keep these at a very high level, and I'll have other videos where we can dive into some of the more specific details for each of these different libraries that we look at. Before we continue on, this is just a quick reminder that I do have courses available on DomeTrain. If you're just getting started in your programming journey and you want to learn C#, you can head over to DomeTrain. I have a Getting Started in C# course. It's approximately 5 hours of content taking you from absolutely no experience to being able to program in C#. And after that, I have my Deep Dive course, which will take you to the next level with another 6 hours of content so that you can start building basic applications. Head over to DomeTrain and check it out. Let's head back to the video. We've talked about being able to be more thread safe, so that's where concurrent dictionary came in. The fast concurrent TLRU is also thread safe, given that it's concurrent, it's great. But the fast concurrent TLRU also gives us a capacity check, and it also gives us the ability to expire. So we're sort of building up on more capabilities that we could use with our cache. But so far, everything that we've been looking at are just these helpful different collections that we can use, not really specific to ASP.NET Core, not really specific to anything to do with web APIs. We're just able to leverage these sort of anywhere that we want. And personally, I've used these certainly outside of web APIs, just different systems that I built. But something that we can start to look at now going forward are a little bit more specific for working with ASP.NET Core. And the next one that we're going to look at is actually built-in. The built-in one that we're going to be looking at is the very simple memory cache. And you can see on line 6 here, I'm using services.addMemoryCache. If you're not familiar with what this is doing, like what's going on here, this is just using dependency injection with this extension method to add a memory cache. And if you're not familiar with dependency injection, I have plenty of videos on my YouTube channel. It's one of the things that I love to talk about because dependency injection is super powerful, especially if you're building plugin systems, which I love to do. But we add that into the services, and that way our application has this service available to us called a memory cache that we can leverage in our minimal API. So if you look on line 11 here, I have iMemory cache, and this works because we've added it on line 6. That means that the runtime will allow us to resolve that dependency for this API here. If we look a little bit lower, we can see that the caching structure looks a little bit different now. It's not just doing a check to get the value and setting it. It actually has this get or create async. So this type of pattern we see here is going to be more and more common as we go forward, and this is supposed to be one of the structures that helps us with what's called stampede protection, right? So the fact that we can ask for an item, and if it's not there, it will use this callback. So let me walk through some of the syntax here because it might look a little bit weird. But the idea is sort of like, hey, if you don't have it, then this is the thing that you're going to use to go create it. So it is very much like what we saw before in the more simple examples. It's just kind of built into how you leverage the API itself. So the first part is going to be the key that we're working with here, right? So just the day of the week, that's going to consistently be the key that we have. But if that entry is not found, what we're going to do is call this what's called a factory method to say, go create the entry that we want to put into the cache. So this will get called only when the item is not in the cache based on this key. The next part that we have here, though, is going to be sort of like what we had with BitFaster caching, when we can actually expire the items that are going in. This is pretty cool that we have access to this built right in. We don't need any fancy libraries or anything, and it's just iMemory cache to go use it. So if I go ahead and run this, so let's stop it, we'll go run it again. We will head over to the browser, and I'm just going to press enter. We should see that the first time, like every time, it's going to take 1 second to get a result back. There we go. And now every time after, until it expires like it just did, right? Keep doing it, and this one will expire, right? So this is basically like we've seen so far, right? I just want to be able to show you, like I said, having these different comparisons so you can have different options and understand the different tools that you have to work with. So let's go ahead and stop that and talk about sort of conceptually something that's a little bit more advanced than this. The memory cache and everything that we've been looking at so far is in memory, right? Like this one is literally called iMemory cache. There are more advanced things built into .NET that we can leverage, and what we're not going to be looking at in more detail is the distributed caching part. We're going to start looking at some libraries, and including another one that's built in, that is for distributed caching, but I'm not going to show you how to go set up Redis in this video. That's going to be way more complicated than I want to get across here. We can do deep dives on that in other videos, but I want to show you and sort of talk about this concept so that as we go forward, you'll understand why caching starts to get a lot more complicated. At a high level, like we've been saying in this video so far, everything that we've been doing for caching is in memory. So we don't have to coordinate our cache with anyone else. We have this service that's running right here on my desktop. When we're calling it, all that's happening is we have this process with items in memory, and some of the advanced features we've seen is that we can expire those items or limit how many items we keep in the cache, and it's thread safe. So this is super helpful when you have one service like this. But what about when you're dealing with multiple services? What happens not only when you have multiple services, so say we wanted to have 5 instances of our weather app, does every single one of them need to have its own cache? Is there a benefit, or is there something else we could do to try and have something like, let's say, a shared cache? What's interesting when we start talking about some of these more advanced caching concepts is that we still have to look at the trade-offs that are happening. You'll hear in different types of systems, you might have different layers of caching. So you might have like what you refer to as an L0 or L1 cache. You can kind of index however you want here, but you can start with an in-memory cache that's local, sort of like in process, kind of like our dictionary, right? Or the memory cache that we have here. These should be extremely fast. The reality is that the cost of the cache is greater because you have it right in process. It consumes memory. If the process goes down, you lose the cache. So there's more cost to it, but it is the fastest type of cache that we have to work with. Then you have these other layers of cache. And what's interesting about these is that these can start to be sort of out of process, or they could even be their own services that are running. And the idea with these is that they're way faster to use than still going to another downstream service, like say having to go run a complicated database query or go process data that might take you a second or more, or whatever it happens to be, or some latency in between here. We can actually take this information and cache it into a dedicated caching service. Now, this caching service can now be shared across different instances of other services. And we can layer these things together, which is really cool. So we can have something that's very fast in memory, and then we could also have this second layer of cache that's shared across different processes or different services altogether. But as you might start to suspect here, the complexity starts to go through the roof. Like, we haven't even talked at all in this video about cache invalidation, right? We've talked about sort of expiring entries, but what happens if someone said, hey, I need to go update this item, the thing that's in your cache is no longer relevant. it might not be so bad if you just control it like a dictionary in memory, but as soon as it's across all these other processes and shared in a service, good luck trying to coordinate that, right? It's very complicated, and there's really advanced services to try and make this more streamlined for you. But the reality is, it's still not easy. It's one of the most difficult things that we have in software engineering. The next cache that I want to look at is just going to be the interface that we're going to talk through, but it is going to be distributed cache, and we're going to build on top of that. So let's go see that. On line 7, what I'm doing is just changing the dependency injection. I'm adding distributed memory cache. This is a bit of a cheat here because I'm not looking at implementations of distributed caches. The most popular one that people will know is called Redis. There's other ones available as well, but you could have something like a Redis implementation of the distributed cache. And then you can see on line 12, I'm now using distributed cache here instead of memory cache. Here's where things get a little bit weird. You'll see that this code here isn't compiling anymore, and that's because there is no get or create async. And the way that we have to work with the distributed cache is with a different API. So if I get rid of that and type cache, if we look at what's available, right, I can get things and I can set things. And what's even more kind of awkward, if I want to get something out of here, you can see that it takes a string key, and then what it's returning is a byte array. The things that I just want to pause to talk about here in terms of the API usage is, number one, we're forced to use a string key. That's not so bad, right? We could go take our day of the week and we could go make that a string. Really, not that much to complain about there. But the two things that are a little bit crappy compared to what we've seen so far, and especially if we've contrasting the sort of evolution of these different caches that we've seen, is that, well, one, this only returns a byte array. We're dealing with, so far, this weather forecast type inside of a list, but now that has to be a byte array. So already what's happening is we need to consider that we need to serialize and deserialize this data. Well, why does that have to happen? It's because we're talking about a distributed cache. We need to take these things from memory and take them and convert them into bytes so we can go send them to somewhere else. This is, like I said, another layer of complexity. Serialization and deserialization is performance overhead. So another reason why something like an off-box cache, so something that's not running locally, might take more time to go do because you have to do these processes. But the other weird thing that we have here is that we have to either get the data, and if it doesn't exist, then we have to set the data, right? So here's the other API. We can use set async. We can put in the key, right? And then we can pass in the serialized data. But if you remember what I said earlier about having to do separate get and set, is it brings us back to this problem of what's called a cache stampede. Just to kind of repeat it, and I realize that for folks that are more familiar with cache stampeding, this is probably not going to do the explanation justice because this is a pretty complicated thing that happens in distributed systems. So what I do suggest you do is when you hear me talking about cache stampedes, please go read more about this online. Look for visual examples. There's other videos online that will explain these specific things more in detail. The whole point of this video is to give you some high-level concepts that you can go drill into. But when we're talking about a cache stampede, we kind of saw this in some of the earlier examples where we sent in all these requests and none of them had access or none of them had that entry in the cache, right? So all of them said, not in the cache? Cool, let me go to the downstream service. When we have this type of API, it forces us to separately get and set things. Some of the other APIs we saw, like the memory one, or some of the other ones we'll see coming up, they actually build this in for you so that the sort of API, the infrastructure, can try to control how many things in parallel can sort of bypass that cache. So just a super quick example, if you had 100 requests coming in, so you have a really heavy service or heavy traffic for this service, of 100 requests that come in, what might happen is 100 of them at the same time go to check the cache. And with this cache, this distributed one, all of them, if it's not in the cache, all of them will check the cache and then go downstream to call that service. So basically all 100 sneak through and have to go downstream to go get data. In our example, that's just 100 of them that have to wait here and kind of sit here on this delay. But in a real system, that could be a database call or some other service, right? Now, with these other caches that have what's called stampede protection, what they are able to do is basically control how many things go through. So maybe not only one is able to go through, and that's because when you have multiple instances, so say we had 5 instances of our service, if you had 100 requests split across those 5 instances, let's pretend equally, you would have 20 requests going to each service, okay? When that happens, each one of those services has stampede protection, and that means that out of 20 going in parallel, what's going to happen is within the process, only one of the 20 is able to go through at a time. So instead of 100 requests in total sneaking through to go downstream, or in our case, 100 of them sitting here for 1 second, what's going to happen is that only 5, one from each of those processes, will go through, and that way you're not having what's called that stampede go through and hit that downstream service. You've very much limited the impact of when something expires from the cache or there's no cache entry. So like I said, if that's confusing, you want to read more about it, I think it's very important to understand if you're starting to build things with caches, especially in distributed systems. If this is just something for you to go build for fun, like a hobby project on the side, and you don't have a ton of traffic, these types of things will introduce a ton of complexity, probably not for a good reason, but if you're scaling up systems or want to understand that, please go read more about this stuff. Distributed cache does not give us that protection. There is something else that we can use that Microsoft has. It's not yet included by standard in the current version of .NET that we have at the time of recording. So it is in pre-release. Maybe if you're watching this in the future, it will already be included, but it's called the hybrid cache. And as you might guess by the name of hybrid cache, it will take the iMemory cache and the iDistributed cache and give us the best of both worlds. So let me go ahead and show you that code. All right, so a couple of things to discuss here. You can see that I have add hybrid cache. I have these pragmas around here because if I go take them off, just so we can see, it's complaining at compile time, right? So it's saying this stuff is only for evaluation purposes. The time you're watching this, if it's in the future, which I think by definition it must be in the future, depending on when though, this stuff might already be included and you don't have to worry about these pragmas. But if you're watching it sort of right after I release this, this is what I'm doing to make it compile. Just to mention as well, if you want this included, you can see that I have this package reference right here, Microsoft Extensions Caching Hybrid. I think in the future, they do plan to include this directly, so you may not need a whole separate package, but you'll notice here that it is in preview. Okay, so I just wanted to get that out of the way so you know where it's coming from. But same idea, we're using dependency injection, we're registering the hybrid cache, okay? And I'm not configuring, you can see like there's no other hidden code here, right? I'm not configuring like Redis or some other distributed caching system. So out of the box, right, it's only going to have the memory one. You don't even see me adding memory here explicitly, but I'm certainly not adding anything that's extra, any other process or anything like that. To use it, it very much is just like that memory cache example we saw, right? I have hybrid cache here right on the minimal API. Again, we can access this because it's part of dependency injection, so we can get this passed in for us. Looking at this syntax here, right? It's not a separate get and set. So this in the signature is giving us that stampede protection kind of API, at least something that will help support it. Here, get or set, we have to use a key. So this one is also using strings for the key of the cache. This is going to be the factory, right? Same pattern that we saw earlier. If it's not in the cache, call the factory to create the item and put it into the cache. And then we have some options. So here what's pretty cool is we have expiration, and this is going to be for the distributed cache part, and then this is going to be a local cache expiration. I don't have a distributed cache, right? You can see there's no other setup here, so we should essentially only be using this 3-second cache. But let's go ahead and run this. We should be able to see that we can get a cache working just like this out of the box. So if I press enter, we should see 1 second. There we go. And if I keep calling it, it's act like it's already cached. But now that I've waited a little longer, you can see that it's taking some time. Cached again and now uncached. There you go. So again, I know some of the examples kind of look sort of boring or repetitive. I'm just trying to show you that we get the same behavior, and that way you can tune these things to your liking. But this is cool because if you wanted to go add a distributed cache now, the best part is that you get this API that looked like the memory cache. That distributed cache will be another layer of cache behind the scenes that you don't have to think about when you're using this cache. And that's really powerful, right? Because like I said, we get the sort of helpful API that we saw with the memory cache, but we have the power to have multiple levels of cache in our applications. Because this hybrid cache, like I said at the time of recording, is in pre-release, it's not yet included by default, there is one more caching library we're going to look at. This is what I've been using in my SaaS called BrandGhost. I may switch to the hybrid one when it's publicly available, sort of like by default. I'll have to see if there's a good reason for me to move over. But this next one that we're going to look at, I've had a lot of success with, and it's called Fusion Cache. To kick things off, you can see if I go to the package references, we have Ziggy Creatures, that's an awesome name, and Fusion Cache. I've just pulled in a preview one, not for any specific reason, probably just because that allow preview checkbox was checked on, and now I'm going to go back to the code and kind of show you what's up with Fusion Cache. I think something that they've done a really good job with for Fusion Cache is that the APIs that they have are very similar to what you have with memory cache and hybrid cache. They've thought about stampede protection from the beginning. They have really good documentation online to be able to explain how you can set up what they call like their backplane for syncing your cache data together. It's super cool. I think they've done a really good job. I'm not being paid to promote them or anything like that, but I'm sharing this with you because I've felt that it's worked really well for my use cases. And if you want something else, another tool in your tool belt, aside from the hybrid cache, this is an opportunity. So very similar, like I said, add Fusion Cache for dependency injection, right? Makes it very nice to not have to configure a lot. With Fusion Cache, and I think probably with the other caches that we have through dependency injection, if you wanted to have different cache instances, like named caches, you can go configure that with cache providers. We're not going to walk through that in this example because it's just a very simple API that we're caching, so nothing to really be concerned about there. But if you wanted to have different caches, you can go do that. But what we're doing here is, like we saw before on line 12, we're basically able to use dependency injection to get the Fusion Cache, and this should look very familiar. I realize, like I said, some of these examples probably seem boring because you're like, hey, it looks the same. That's kind of the point, is that they've done a really good job making these very helpful, familiar APIs, right? So get or set should help us with stampede protection in terms of how they've designed this. So that's great. You can see that they have the factory method to go create something if it's not in the cache already. And then we have cache options as well. So you can set the duration. There's other things too, like there's fail safe. So you can decide or tell your cache if the sort of the factory method throws an exception while you're trying to create the thing. Should it allow you to access the previously cached thing? Should it sort of clear the cache? There's different behavior. So a lot of this stuff is very tunable. Again, I will have other videos on this stuff, but this is really all that we have to deal with. And if I'm going to go press play, we can go check in the browser and see hopefully the exact same behavior. So this one is every 5 seconds. I just have to remember that. So that was 1, right? If I keep pressing enter, it's cached. If I wait just a little bit longer and I press enter now, we should see that it has to go calculate it again. Spinning. There we go, right? So the whole point is that it does work the exact same. And we didn't go run this, this code that frequently throughout these examples, but because we're ending off on Fusion Cache, let's go basically blast our API and see if Fusion Cache can keep up with it. Like I said, I think some of my examples are kind of bad here for the timing just because we're doing it from the same process. But we should start to see some of these coming back. So yes, I know some of these are pretty high, but we can already see some of them coming back. If we were to maybe get rid of the duration, right, we just keep things in the cache. Because if you think about it, while that's running, things are getting removed from the cache. Let's go back and watch. If I did this from a separate process, we probably wouldn't see so much delay, but let's get a little bit lower here. Right, once we start leveling off, we should see fewer of these ones coming in with these high times. But I think a better way that I could have sort of put these examples together, and I apologize, I'm just trying to do it for convenience, is I should have made a second process that I could have kicked off and then just run it against. There's probably some way to do this in Postman very easily, or there's probably other tools for generating traffic, but I thought I would take a shortcut just to make it simple, but I realized that can make some of the examples a little bit confusing. And I also realized I was probably highlighting the port sometimes, which is even more embarrassing. So anyway, I think we should probably be able to see that aside from the very beginning here, we have pretty good... like that's a pretty high latency, but if I scroll down lower, high latency still, high latency, but we start to get into this territory where the latency is very low. These ones are still pretty high, but I hope you get the idea, right? It's like when we're kicking off all of these things at the same time, like the process is, we're only able to run so many threads at the same time. So some of these things are a little bit more delayed, but this, like I said at the beginning, is a bit of a hack, but the idea, hopefully, that you saw is that we have these very similar APIs to use when we're working with these different caching libraries. Personally, the one that I've been building with for the last little while is Fusion Cache, and I think that I will try to explore the hybrid cache from Microsoft as soon as it's sort of included by default and no longer in pre-release. Hopefully you found this helpful. I will try to add more videos into the playlist around caching so you can explore that more in depth, and that way this tutorial that's already sort of close to an hour, you don't have to watch a full hour's worth of content, and we can start drilling into more specific situations that you'll want caching for. So thanks so much for watching, and I'll see you next time.